viewers, welcome to my channel. My name is Johannes. In this tutorial session, we are going to solve gradually varied flow profiles. So I think once we set out the learning objectives of this chapter, it is just to classify the water surface profile and to evaluate the length of backwater curve. So let us see these examples in detail. Okay, let's get started now. Example 3.1 GVF type profile. A rectangular channel with bottom width of 4 meters and bottom slope of 0.008 has a discharge of 1.5 meter cube per second. So if a GVF in this channel is produced, the depth at a certain location to be 0.3, assuming Manning roughness given as 0.016. Then determine the type of GVF profile. So you are going to determine what type of gradually varied profile. So I think as the name implies, gradually varied flow profile is just gradually varied flow is a steady state, a steady non-uniform flow where just the depth varies gradually along the channel. So find Y naught and YC first, normal depth and critical depth. So from Manning's equation, I hope you know this equation, Manning equation, Q is equal to A over N, R total, S naught, the power of half. Then once you have this, then we have just derived this equation from the previous slides, from the previous videos. Just the Qn over radical S naught b the power of 8 over 3 is equal to N naught over 5 over 3, 1 plus this 2 naught to N naught, the power of 2 over 3, where N naught is Y naught over B. Then you have just you can substitute now the known values. Q you can substitute, N, etc. Then you get this expression. Then how do you solve this? Just by iteration, we will try. So once you have this simplified number, then you just multiply by the whole exponent 3 over 5 on both sides. Multiply by 3 over 5 on both sides, then you get this expression. So this is the expression to be calculated. Type say 0.6 in your calculator, then save it in your calculator as answer. Then just we will just write in your calculator this expression. Then you simply click just again and again. You just click again and again until you get constant number. So that constant number will be your final iteration. So this is N naught. So once you get N naught, then you can find Y naught. So N naught is equal to Y naught over B. So normal depth will be 0.426. So once you find normal depth, then for rectangular channel, we know that critical depth is given by this equation. Clear? Critical depth is given by this equation. Q square over G V square, the whole 1/3. Then you substitute the known values, then you get 0.24. So we are going to compare critical depth and normal depth. So since YC is less than Y naught, which is critical depth is less than normal depth, the channel is yield slope channel. And as YC is less than Y naught, the profile is M2 type. Let us see the profile. So the profile is like this. So the depth is like this. So normal depth line is larger than critical depth. So it is in this region. So in this region, you have yield slope channel and M2 profile. So this is M2 profile because YC is less than Y naught. So I hope this is clear. And the other problem is water surface profile of GVF. Let us see. Find the slope of water surface profile of a GVF in a rectangular channel, 15 meter wide and 3 meter deep. The slope of the channel bed is given. The bed slope of the channel 1 to 5,000, and the total flow rate or discharge is 29 meter cube per second. Assume chassis roughness 65. Is the depth increasing or decreasing in the direction of the flow? So you are asked just the slope of the water surface and also the flow nature or how the depth is changing with respect to the longitudinal direction. So you have just solution, just area is equal to B times Y because the rectangular channel, we know rectangular channel. So if you have the B, then if you have Y, then you can find V times Y. So this is area, perimeter again, V plus 2Y, the perimeter of this water. So the perimeter of this water is just V plus 2Y, because you have here again Y. So the periphery of the channel, which is touching by water surface, by water. So you have 21 hydraulic radius area over weighted perimeter, you get this result. Then using Chasey equation, you know Chasey, if Chasey roughness is given, you will use this equation for flow rate. Otherwise, if Manning roughness is given, you will use Manning equation. So from this, you can find SF, which is slope of energy line. So the slope of energy line will be just square both sides, you get this equation, Q square over C square, A square times R. So you get this. This is the slope of energy line. Then we will compare with bed slope. Then first find V, which is the velocity Q over area. You get the velocity of the flow, which is 0.64 meter per second. Then to find the flow region, you can find the Froude number. So calculate the Froude number by this equation. V is equal to G square root of G Y. So V over square root of Gy. This is for rectangular channel. Otherwise, this Y for other channel, you will not use Y. You have to use D. So D is hydraulic depth. So D is given by area over top width. You know this from the previous examples we have completed. Area divided by top width only. You will calculate for triangular channel, for trapezoidal channel, or for other channel. You have to use hydraulic depth. So you just substitute, then you can find this is the result. Froude number is less than 1, then it is subcritical. Subcritical. So the flow is said to be critical if the Froude number is equal to 1. Otherwise, if it is greater than 1, it will be supercritical. So this flow is subcritical. So let's calculate now dy by dx. dy by dx, which is a gradually varied flow equation. So I think one of the learning objective of this chapter is just to derive the equation of dynamic equation or the equation of gradually varied flow. So you just substitute the known values in the calculated values, then you get this is plus. So just positive over positive. So let's see. Then calculate critical depth for this rectangular channel, Q square over GB square, so whole 1/3. Then we get 0.725. Since YC is less than Y naught and S naught is greater than SF, since this is S naught, bed slope is greater than SF, the channel is yield slope channel and the profile is increasing. Clear? The profile is increasing downstream with X distance. So it is M1 type. It is M1 type profile. So this is the profile. So you can see the depth is increasing, which is just the profile is increasing, and S naught is more than SF. Then since you have YC is less than Y naught, so it is just in M1 type profile, because just the depth is increasing because this is positive over positive. So I think you can find. So don't forget the type of profiles in the previous topic. We have y by dx equal to 0. The slope of water surface is equal to bottom, just equal to the bottom slope. S naught is equal to just SF. So clear, uniform flow will attain. Otherwise, if dy by dx is positive, then an increase in depth along the channel. So we using this, just we can say the depth is increasing. Otherwise, if it is negative or less than, drop in water surface will happen. So I think the types of GVF profiles, yield slope means you have 3 regions, M1, which is Y greater than Y naught, greater than YC, M1. And also if Y naught is greater than Y, then greater than YC, M2 type, otherwise M3 type. So we have yield slope, steep slope, critical slope, and horizontal bed and adverse slope. So these are the type of gradually varied flow profile, along with the channel type and the type of profile. Just the type of profile is just the depth is increasing, then you can find M1 type. And the third example is flow profile. Flow profile. So you have a rectangular channel 4.5 meter wide having a bed slope of 0.009 carries water at a depth of 1.4. So depth is given here. Now what is just the required. If the channel terminates an abrupt drop in the bed of the channel, what type of flow profile upstream of the drop is expected to be formed? Upstream of the drop, assume n is this one. So just a channel just came across with this one, like this drop. Then what type of flow profile you are going to expect? So what will be the type of flow profile? So for rectangular channel, B times Y will be area, and perimeter B plus 2Y as usual. You get this result. And hydraulic radius area over weighted perimeter, you get 0.863. So using one equation, now you can find the discharge or the flow rate which is passing through the channel, which is A over N R2 sir S radical S naught. Then you can find 10.707 meter cube per second. So this is, I think, the channel discharge. Clear? Once you find the channel discharge, then you can find other parameters again. V is equal to Q over area. So the velocity of the flow is 1.699 meter per second. Then find for rectangular channel, you will use this is V over square root of Gy. But for other type of channel, this Y will be D, hydraulic depth, which is area divided by top dimension. So after substitution, you get this result. So this is less than 1. It is subcritical flow. Subcritical flow. So we know just the flow region. Then you can find now the critical depth using this one. For rectangular channel, Q square over GB square, the whole 1/3. So this is just the critical depth, 0.8325 meter. Then let's find now from the relation, which is Chesy. Just we know this is already, we know Chesy and roughness relationship. Hydraulic radius to the power of 1/6 over N. Then you have this. This is 60.9. Then from Chesy equation, we know this equation. Slope of energy line will be this one. Q square over C square A square times R. Then you get this is the slope of energy line. Clear? So flow rate we have computed using Manning roughness, using Manning equation, and then slope of energy line should be computed using Chesy because we have this relationship. C is equal to R to the power of 1/6 over N. Okay, then dy by dx, this is a gradually varied flow equation. We know this equation. Then after substitution, you get positive over positive. This will be positive. So I think now since y naught is greater than yc, since normal depth is greater than yc, and s naught is greater than sf, then Froude number square is less than 1 in this equation. So you get positive over positive. So the channel is mild slope channel. Clear? The channel is mild slope channel. And the type of the profile is M2 type. And the depth is decreasing. The depth is decreasing. Let me show you. This is the profile. So M2 profile. So the depth is increasing from Y0 to YC, to critical depth along the channel. So I hope this is clear. So now let's go to the last example, length of water surface profile, the length of GVF profile. So I hope one of the learning objective of this topic is to determine the length of backwater curve. So let's see, a rectangular channel with bed width of 2.5 meter has a discharge of 10 meter cube per second laid at a slope of 0.001, and Manning roughness will be this one, 0.015. If the upstream water depth is 2 meter, and downstream depth is 1.6 meter, estimate the length of water surface profile between the two sections, neglecting energy loss. So given Q, given 10 meter cube per second, bottom dimension 2.5, and bed slope 0.001, and Manning roughness given, and Y1 given, and Y2 given. Required delta X. Let me draw. So you are just going to calculate this length of X. So the length of water surface profile, let us calculate. So first you should determine A1, which is the cross section in this one, which is in first one, which is this is 1, this is 2, clear. Then A1 will be 2.5 times 2, since it is rectangular, B times Y, 5 meters square. P1 you calculate. A2, B times Y2, this is 4 meters square, and P2 will be this one, B plus 2 times Y2. Then hydraulic radius, you will calculate A1 over P1 for both. This you get this one. Then from Q is equal to area times velocity, you can find V1, the flow velocity, which is going through cross section 1. So this is cross section 1. This is cross section 2, clear. Then find V1, which is 2 meters per second, V2, 2.5 meters per second. Now let's continue now. The specific energy can be found as using specific energy calculation, using specific energy formula. So E1 will be Y1 V1 square over 2G. You get this result. This is the specific energy at cross section 1, and the specific energy at cross section 2 will be Y2 plus V2 square over 2G. You get this result. Then just let's go now. The mean velocities and mean hydraulic radius of the cross sections will be mean velocity V1 plus V2 over 2. You get this result. This is R1 plus R2 over 2. Then you get this is the average hydraulic radius for both sections 1 and 2. Then the slope of the energy line is given by, this is using Manning equation. If Manning roughness is given, you will use this equation, mean velocity square n square over r mean the power of 4 over 3. So you get slope of the energy line will be, this is the slope of energy line. Then once you compute this one, the length of water surface profile is given by this equation, clear, this equation. Then after substitution, just delta x, which is E1 minus E2 over average slope of water surface, slope of energy line, minus S naught, already average, already computed. Then after substitution, you get this meter length of water surface. So I hope this is clear. So I think thank you very much for watching this video. If you have any question or doubt regarding this tutorial problems, please forward through comment suggestion box and I will reply on it. So thanks again.